So the next, actually last year I split 11.4, which deals with binomial experiments. I split it into 3 different lessons. That'll probably be the same case this year. Today is just identifying a binomial experiment, and then the next couple of days would be kind of setting up a binomial experiment and then working with calculations for binomial distributions. So you have to understand what a binomial experiment or binomial distribution is, and that's what today is identifying if it even is binomial. So what I have at the top is an example of what would be a binomial experiment, or a binomial, what would come out as a binomial distribution. It talks about a multiple choice quiz. So it says each question on a multiple choice quiz can be thought of as a trial with 2 possible outcomes. Either you get the question correct or you don't. If a person were to guess on each of 5 questions, the probability that he or she answers a question correctly would be the same on all 5 questions. So the probability of getting each question correct would be the same. So answering the first question doesn't change the probability that they're getting the second question correct, is what that means. So it says guessing on each question is an example of a binomial experiment. So a binomial experiment is a probability experiment that satisfies these conditions. And so these are the conditions we are going to be referring to as we answer the questions today. And it's purely identifying, is this a situation that could be a binomial experiment? And then if it is, you're identifying certain information. If it isn't, you're explaining why not. So in a binomial experiment, there has to be a fixed number of independent trials n. And I'm going to, once I read through this list here, I'm going to come back and talk about what that independent means for independent trials. So if I kind of refer back to this multiple choice example, if there's 5 multiple choice questions, the n value would be 5 in that example. Each trial has only 2 possible outcomes, success or failure. So a trial in this example explained above would be answering a multiple choice question. A success would be getting the answer correct. A failure would be getting the answer wrong. But I do want to say success or failure doesn't always mean something's correct or something's wrong. The success would be the outcome you're looking for. A failure would be the opposite outcome. So say you have something that deals with males and females, and you're choosing only males for something. A success then would be choosing a male, and a failure would be choosing a female. So the success just identifies the outcome you're looking for, not necessarily right or wrong, or what you would normally consider a success or a failure. The probability of success is always notated with the lowercase p. So if you see p, that's talking about the probability of a success in a binomial experiment. And that probability of success is the same in every trial. So like I explained above, the probability that I'm going to get the first multiple choice question correct is the same as the probability I would get the second multiple choice question correct. So how I answer the first one doesn't change my probability of getting question 2 correct. That is what independent means. So when it talks about independent trials, that means every trial has the same probability of success. If you have a situation in which your probability of a success changes from each trial, then it's not a binomial experiment. And the probability of failure, they call Q. So eventually in a lesson, we're going to see a formula for actually calculating a probability of a binomial distribution. Probability of failure is represented with the letter Q, and it's calculated by taking 1 minus P, the probability of success. And then the random variable X is the number of successes in N trials. So N represents the number of trials that are happening in the experiment. So in the multiple choice example, if there's 5 questions, N would be 5. So it does say many probability experiments are or can be reduced to binomial experiments, and that's what we are identifying today. So in these examples, we're determining whether each experiment is or could be reduced to a binomial experiment? And if yes, if so, we are going to describe what a trial is, what the random variable is, and state the number of trials n, the probability of success p, and the probability of failure q. And then if it's not, we have to explain why not. So I'll point out as we go through these things to look for as you're identifying this. So letter A, it says, in a class that consists of 12 male and 13 female students, a group of 5 students is randomly chosen to see how many males are selected. Okay, so in kind of looking at this list up here, these are things you need to make sure are actually happening in the experiment for it to be a binomial experiment. There has to be a fixed number of independent trials, n. So here they are choosing 5 students. So a trial would be choosing a male student, and there's 5 trials. They're choosing 5 students. So there would be a fixed number of trials. We'll come back to see if they're actually independent or not. Each trial has only 2 possible outcomes, and that's true here as well. The student they choose is either going to be a male student or a female student, so those are your 2 possible outcomes. The success would be choosing a male student because we want to see how many males are selected. A failure would be choosing a female student. And then it says probability of success, which in this case the success would be choosing a male student. The probability of success is the same in every trial. So this is really what you want to look for. If you get to this point, make sure that your probability of a success for every trial is the same. And here's how you can determine that if you're not sure. So first of all, probability we've talked about as being the frequency out of the total number of possibilities. So if I have 12 male and 13 female students, altogether I have 25 students. And I'm choosing 5 students. I want to see how many males are selected. So by choosing the first student, what would the probability be of that student being a male? So the first student I choose, what's the probability that the student will be a male? 12 out of 25. Okay? So here's what you have to think then, is the probability of choosing a male student 12 out of 25 for all 5 trials. So let's say that first student I chose ends up being a male. Okay, so yes, the probability was 12 out of 25, and yes, the student that was chosen was a male. So now when I choose the second student, is the probability still 12 out of 25 that the next student will be a male? I see some no's. How many males are left? Or Cora?
So when they're chosen, are they taken out?
They're taken out, yeah, so they're not put back in. Yes, so the next probability of choosing a male, if the first one was a male, would be 11 out of 24. Even if the first student I chose was a female, the probability would still change because I now only have 24 students. We're not putting the students back because we're choosing 5 different students. So this is a case where the probability of success is not the same in every trial. The probability of choosing a male student changes after every trial. So therefore, it is not a binomial experiment. Okay, so here's how I'd like you to explain this. I'm going to say this is not a binomial experiment because, exactly as I had explained, the probability of success changes after each trial. Probability of success changes after each trial. Okay, so that's an example of where it would not be a binomial experiment. I will say, too, that second bullet point that I went through, where you only have two possible outcomes, if you're ever given a situation where in one trial there's more than two things that could happen, or there's more than two outcomes, that would be a reason for it to not be a binomial experiment. So this isn't the only reason it couldn't be. It's if any of these conditions above are not met. Okay, are there any questions on A as to why that's not? We'll obviously be seeing examples that are, so that will help too, so you know what one is. Okay. So then if we look at example B, it says a school study found that 65% of students have seen an episode of a specific show. 7 students are randomly asked if they have seen an episode of the show. Okay, so to put this in perspective, what's happening, it says, if I go back up to these bullet points, there's a fixed number of independent trials n, and again, the independent we'll have to look at. But I'm asking 7 students, that's a fixed number. A trial would be asking a student if they had seen the show, and I'm asking 7 students. So there is a fixed number the independent will have to look at. Each trial has only 2 possible outcomes. So when the student is asked if they can see or if they have seen the show, they're either going to say, yes, I've seen the show, or no, I haven't. So there's only 2 responses they could give, yes or no. A success would be that they have seen the show. A failure would be they have not seen the show. So here's where we kind of stopped in the last one. Probability of success is the same in every trial. So it says 65% of students in this school have seen the episode, and they're asking 7 specific students. Because of this percentage, that means the probability that a student will have seen the show is going to be 65%, or 0.65. Now, if I ask one student, have you seen the show? And then I ask a second student, is the probability, or is the first person's answer going to affect the probability that the second person has seen the show? No, their probabilities are all going to be the same. So here, a success has the same probability every time, so this probability of a failure is the same every time. And then the random variable would just be identified. So this isn't really a deciding factor in whether or not we actually have an experiment. We just have to say what the random variable is, what the measurement is. So part B, example B, is a binomial experiment. So I will say here, this is a binomial experiment. And then I have to go back to the directions and just list what the problem was looking for. So it said, if it is, describe a trial. So I have to say what a trial is, and I know I had already talked about that. So in this case, if they're seeing, or if they're saying 7 students are randomly asked if they have seen an episode of the show, the trial is actually asking the student. The trial is how you're going to get the data. So a trial is asking a student and then it says determine the random variable. And random variables you've determined before, that's the numerical outcome of an event. And the random variable is the number of successes. So the random variable here would be the number of students that have seen an episode of the show. So I'll say the random variable is the number of students who have seen the show. So your random variable should always represent a number of something, or be a numerical value. And then it says state N, P, and Q. So I'll just put here and, N equals, so N is your number of trials, so they are asking 7 students, so N would be 7. Okay, and identifying these values as we move through this section is going to make more sense when you're actually calculating. You would need to know the values of N, P, and Q. We're just not calculating anything today, but identifying these now will help later when we do have to do calculations. P is the probability of a success, so the probability that a student has seen the show, and that would be 65%. Write it as a decimal though, so it would be 0.65. And Q then is the probability of failure, so it is 1 minus the probability of a success, and so 1 minus 0.65 means there's a 35% chance, or 0.35 is the probability that somebody has not seen the show. Okay, so it's really just being able to understand with the conditions on the experiment if it is binomial or not, but then also being able to identify these three values. Okay, questions on part B? Okay, so I would like you to take, we'll say, a few minutes here and look at examples C and D, and just look through them, think about whether or not they would be binomial experiments, so kind of go through that same thought process I showed for examples A and B, and then we'll make sure we go through them together as well to make sure you have things correct. But if you're saying it is binomial, then you should be able to identify what we identified for part B. If you're saying it's not, you should be able to give a reason as to why not. And you can discuss it with one another as well. If you do get through the two examples and you're kind of waiting, the 4 examples for the extra practice are on the back. You could start looking at those as well.
Or is it what's
The random variable is always going to be the number of successes. So if 75 students are randomly asked if they own a car, a success would be considered if they say yes, they own the car. So the random variable then would be the number of students who own the car. Okay, I know some of you are done. Some of you at least have had a chance to look at them. Maybe you're still kind of thinking through it. And I just have the information up here we would be looking for if it is. So I'm not saying that both of these are. Would somebody like to share what they came up with for C, whether or not you said it was, and then if you said it was, what you said this information was, if you said no, why you said no? Anybody have example C, whether or not that would be a binomial experiment? You said it was? And if you said it was, what did you say a trial was? So a trial would be asking the students. What did you say the random, so X here would be the random variable. What did you say the random variable was? And then what about N? P? And Q? All right, so yes, I would agree. C, example C, is a binomial experiment. There's only two outcomes. A student is either going to own a car or they're not going to own a car. And the probability that each student owns a car would be the same. What about for D? If 4 cards are removed from a deck to see how many aces are selected. So they're removed, but they're not put back.
I said that it's not a binomial
experiment
because the probability of each success changes with each particular card.
Yes, so it's kind of like choosing the students in example A. After you choose your first card, the probability of choosing an ace is going to change because you have one less card. You may have one less ace at the time. So we wouldn't be filling any of this in for example D. What Lily had said was correct. Make sure you have this written down. I'm just going to save time and not write it. But it would not be a binomial experiment for the same reason as example A. The probability of success would change after each trial.